defined in microwave tokens. And we're supposed to devise a method and give a correlation between two parameters. They're the jump height of the corn kernel and the properties of the sound that it actually emits when popping. So the first thing we are going to have to do is find what that bursting temperature is. So we run corn kernels on copper bench and try to understand what the distribution was and at what point would the corn kernel actually start jumping. And on average we'll find 180 degrees, which is practically what is found in other points in the literature. So we're very comfortable with that value, and this is what we're going to use in most of our experiments. Basically, at that temperature, what we observe is a change in all the properties of the pop form. One of the main problems is that even though the radius itself increases, the distribution and the order of magnitude of the values increases a lot. This is not on scale, and now you have the scale. So basically, this phenomenon and this distribution that we have here makes us want to go to this problem with a statistical approach, because due to the random factor that is inside every corn kernel, and due to the fact that we cannot control how they're going to be manufactured, produced, and how they're going to be when we actually get them in our hands later on after buying them, there's going to be all the time that distribution and randomness problem. So we're actually going to try to find what the occurrences of the jump heights are, and our first idea is going to go through an energetic approach. So basically, the corn kernel has a certain energy that is given by the temperature. It is going to emit probably the energy of the sound, and it's going to have a certain energy on the jump, which is composed of its 2D kinetic energy and the rotationary energy. And we're going to assume that the corn kernel is a sphere. Basically, we found that we had a lot of parameters to take into account. First of which being the heating specifications and the dispositive that we actually use to preheat the popcorn. So we have a very awkward popping percent depending on what we're actually using and the state of the corn kernel itself. What we tend to observe is that it cooks best when you actually flip it on the sides, just like the crack was. And we tend to observe that coupling tends to reduce the jump height. So in most of our experiments, to make the problem even more annoying, we're actually going to take corn kernels one by one. The kernel's state itself depends on many actual properties, and we tend to find that the popping percent is slightly related to the percentage of water that is inside the corn kernel. And the first thing we would like to know is, can we actually observe water during the jump? So this is what we can observe at a high-speed camera. We see a bit of water that is emitted at a certain time. It goes off scale because this is not the right video, but it doesn't matter. So yeah, we should see something that is related to water in this presentation. For the jump itself, what we found is that it's very similar to a standard parabolic jump for the vertical speed, and the horizontal speed tends to be linear. In which case, what is actually interesting is the angle of rotation of the corn kernel during its trajectory. So by analyzing every image, we actually find on average that the rotationary angle follows that law and is in green. We should expect a rotationary angle that is around 700 in theory, and the angle we have of rotation at the end is around 600 on average. So, considering the random factor in corn kernels and the ability of jumping and what we saw previously to heating specifications, I would say both of these values are very close to each other. Now, let's move on to the sound itself. We actually tried to 3D design the corn kernel to make it a whistle and to try to find how would the cavity structure influence the sound itself. And on that, we found three possible origins for the corn sound. First of which being the cracking fracture, which is the first thing that we see happening in the video. Then we see pressurized water vapor out of the corn, and then we know that the corn is going to rebound on the ground at one point. So we take a sound sample, which is 23 millisecond long, and the starting origin is the jump. Now we know from the video that the jump takes, let's say, 500 milliseconds, 0.5 seconds. So it cannot be the jump. And if we look on the pulse itself, and we actually estimate the time it takes for the corn kernel to fracture, we know that it's not a possibility. So the only origin we can assume from the correlation between the sound and our video experimentation is that the jump originates from the release of pressurized water vapor. Now, if we take several corn kernels, what we observe in are similarities in the way the signal actually looks. These lengths are all 7 millisecond long on the past stem cells, and the first two jumps very close height, and the last two jump very close height. So from this, our theory that it is connected to the energy should be valid. However, if we start drawing relative energy and relative height, we find that the correlation is extremely poor, due probably to the randomness of it. So we're going to abandon that correlation for now, because it's probably not going to be good, and we're going to go to treatment of the sound signal. Well, too bad. The sound signal is actually very close to the pulse, so we're expecting boxes for the Fourier transform, and we cannot actually, from these examples, guess a Fourier transform correlation. So we're back to this slide has a problem. We're back to the sound and trying to qualify quantitatively what we hear. And from what we hear, and I don't have the sounds here because I don't have a sound input, we would have an average relative height in which we can put the corn kernels in our statistical approach. So the sound can be loud and clear, like this, which is something we can observe. Creasy or creaky, which I can't do, but it's a crackling sound. It can be slightly dull. We can actually hear shh, like the water release of the sound. We can hear a cracking straight up sound. And sometimes we have long sounds, which all of them tend to have effects on the jump. Which leads us to another transform that exists in the theory and study of pulses, which is this wavelet transform. So from here, what we know is if I take the signal of corn with another height, let's say this one, we have actually very close signal forms. And we have a difference in the absolute wavelet of coefficients. We have represented here. What you have to see is the luminosity of each parameter. Now, if we take the same height, we can observe a sound that is very different, but the absolute wavelet of coefficients looks approximately the same in terms of luminosity and intensity. So this is actually going to be our parameter and our correlation. What we're going to say is that the sound is created by the release of pressurized water vapor. That wave comes from the interference and the interaction of every single pressure wave that comes from every single cavity inside the popcorn. And each of them contributes to a term in this thing, which would be the transform of the wave that we obtain at the end. This is our correlation, which apparently is not mathematically, like there's nothing mathematical to it, but the wavelet increases as long as the height increases. And if we actually zoom in slightly, we can see that it corresponds more or less to mathematical functions. This one is very close to be linear for short heights. And so this would be our prediction. We're predicting a bit lower from this Kiviat diagram. We're predicting a little bit lower than what the corn kernels should be for a smaller height. It's because some corns tend to roll and not actually jump. So an additional parameter is going to be the knowledge of the jump itself. Now let's sum up. We have this correlation, which is going to be probably our response. The uncertainties can come from the sound measurement itself. The corn that we buy, that can actually be in a very poor quality. We have an initial dampening that we cannot very much control, but we saw that it had a very important influence. There are a lot of heating irregularities due to the way we actually heat the corn kernel, and the pop is slightly random, because sometimes, and you would know if you've done the experiment, the corn kernels do not jump. So in overall, this is our response. The correlation, if you give me a 2% tolerance, is I will have 50% chance of finding you the proper height with a 2%. If you tell me that the corn jumped or not, I'm going to have a more likely chance to find an answer to that. If you actually give me 10% tolerance, then I'm actually going to be quite close on the actual jump itself. So in conclusion, what you have to give me, and all methods to the answer to that problem is, you give me a sound signal, I'm going to do the wavelet reposition the signal, I'm going to use the chart, and I'm going to have a certain uncertainty. And if in addition you actually tell me that the pawn jumped, then I'm going to have this uncertainty.